Hello and welcome back. In this video we'll finish up section 2.6 on inverses, and we're going to look at an example, and hopefully this will generalize. This example is the function f of x is equal to x squared plus 1. And if we graph this, this is just the function of f of x, but because we've added 1, we've shifted it up. And we see that this doesn't have an inverse. There's a couple of ways to do this. The quick way is to graph this and look and go, oh, this horizontal line intersects the function at two different locations. It does not pass the horizontal line test, so it has no inverse. The other way to see this is that if you plug in two different numbers into f, you can get the same thing. So for instance, if I plug in 1 into f, I'll get 1 squared plus 1, which is 2. But also, if I plug in negative 1, I will get negative 1 squared plus 1. Negative 1 squared is 1, plus 1 is also 2. So since our function maps two different things to 2, f inverse should take 2 back to where it came from, which is both 1 and negative 1. Well, you can't have a function give two outputs, so this is impossible. Again, this is the same thing as saying that a horizontal line intersects the function in two different locations. So this function doesn't have an inverse. But what about if we do the same function, but we only drew 1/2 of it? So we restrict the domain, meaning the domain is all of the x values that we can plug into the function. So when we're looking at all the x values, let's just restrict ourselves to the positive x values. And when we plug those in, we get this function that is just half a parabola. So again, here was the original drawing, and we have this parabola which has a horizontal line will pass through it twice. But if we only draw the right-hand side of this, if we draw the same function, so this is still f of x is equal to x squared plus 1, but we only draw the right-hand side of this, as in all of the x values that are greater than or equal to 0, we now have a function that passes the horizontal line test. It only ever intersects once. So this function, even though it has the same formula as what we did before, this has an inverse because we're only plugging in certain values for x. So let's find the inverse of this function, and we'll only plug in the positive values for x. So again, what we'll do to find the inverse, we will replace f of x with y. So we'll think y is the output, x is the input, and we're only inputting x's that are greater than or equal to 0. So to find the inverse, we switch our inputs and outputs. So we switch our x's and y's. And now we want x is equal to y squared plus 1, where all of the y values are greater than 0. And then we can continue this. I can subtract 1 from both sides. And then I can take a square root of both sides. Now, normally what we would get is y is equal to the square root of x minus 1, or y is equal to the negative square root of x minus 1. However, y has to be positive, so this doesn't exist now. We're not considering when y is negative. So we only have one solution, and there it is. So the inverse function, so f inverse, is going to be the square root of x minus 1. We get to ignore the negative because we know that y has to be positive. So this is just an example of coming up with the inverse of a function that wouldn't normally have an inverse, except we cut off the domain. We only consider part of the domain. And here, I can graph this function as well. I know what this looks like because everything is just reflected about the line y is equal to x. So this function will look like this, half of a sideways parabola.